Hello everyone and welcome back to this next lecture in the machine simulation video series, and this is where we had left off in the previous lecture where we had taken the single phase equivalent circuit of an induction motor, and this is specifically of a single phase squirrel cage induction motor, and we had talked about how we can use the no load test to estimate some of the parameters of the equivalent circuit. And we had specifically stated that using this no load test we can estimate the magnetizing inductance and the core loss component of this equivalent circuit. So there are two parameters which we can estimate using one particular test, that is a no-load test. So in this lecture, I'm going to talk about the blocked rotor test and what we can do with the blocked rotor test. So as always, before I start the lecture, a little bit of brief background that if you're interested in these kind of video lectures, but you would like something a little more comprehensive, I have full-length online courses that you can access on my own website, which is pythonpowerelectronics.com. The name of the project followed by .com. This is the home page of the project, and as you can see, there are 4 buttons: download, learn, watch, read. Learn is what you can click to access the courses which I have currently. So these are the list of courses which I have. And as we can start expanding, the very first course is simulating power electronic circuits using Python, and in this I talk about the basics of how you can simulate power electronic circuits using Python and Python power electronics. The next course is basics of digital signal processing for power engineers, and in this I talk about how you can use Python and specifically the SciPy module and the signal package within the SciPy module to implement and analyze filters for power engineering applications. The third course is simulation of magnetics for power electronics using Python, and in this I talk about how you can simulate inductors, coupled inductors and transformers using Python and Python power electronics. And the fourth course I have is control analysis with Python for grid connected converters, and in this I talk about how you can use Python and the Python control package within Python to analyze and design controllers for power electronic applications. And all my examples are performed using the case of a single phase grid connected converter. The very last course which I have is a free course called Why Specialize in Power Electronics, and this course is more of a motivational course designed more for either young undergraduate students or even high school students who are looking at which engineering domain they wish to specialize in. The idea is to give students who still have not chosen their specialization a background on power electronics, what are the challenges and the possibilities that are available in power electronics, and most importantly, what kind of job opportunities are available. So all these courses are available on 2 platforms, which is on Udemy and Decibel Labs. So you can check out either of these. If you click on the button, it should take you to the link. The link for this page is in the description of this video. So if you're interested, please do check out the description of this video. So with this, I'll get back to my lecture. So this is where we were in the previous lecture, where we had taken this single phase induction motor equivalent circuit. So now the question is, after this no load test, we still have a few parameters that we need to know. The voltage source is independent, so we don't have to do anything there. What we need to do is we need to find out this winding resistance of the stator, the leakage inductance of the stator, and the rotor reactance, right? This rotor reactance is largely the rotor leakage reactance, because again, we are including the leakage of the induction machine into the stator leakage inductance, because remember, it is a stator which is energized and it is a stator flux which is being associated with the rotor through the air gap. So therefore, all leakage that happens in the stator itself, right? Now, and of course, we need to know the rotor resistance. So therefore, now let's talk about what we can do with the blocked rotor test. In the open circuit test, or rather the no load test, it's not the open circuit test, it's a no load test. For a transformer, it's a open circuit test. For an induction motor, we perform a no load test. In the no load test, we run the motor at rated voltage at no load. So the only load which is there on the rotor is the rotor inertia itself, right? Which is very low, because typically a motor is designed to perform a certain amount of task, that it could be a pump, it could be it could be something else. That load is usually the significant part. The inertia of the rotor is usually much lesser than that of the load which is expected. So at no load test, we assume that this slip is almost close to zero, and therefore this branch is open circuited. This leaves only this branch. Now in the blocked rotor test, what we do? We block the rotor. That is, we clamp the rotor so that it cannot rotate. Right? This is done physically. So it's done physically where we clamp the rotor of the motor using any kind of arrangement. Usually there are clamps that are available. Otherwise, you can also use some kind of a belt arrangement if it's a small motor. Of course, for large motors, it would have to be a special arrangement. When you block the rotor, you are making this slip s is equal to 1, because remember, slip is defined as the synchronous speed minus the rotor speed divided by the synchronous speed. If you block the rotor, this nr is 0. If nr is 0, this slip is 1. And if this slip is 1, this entire rotor resistance appears as it is in the circuit. Alright, so now the question is, what will happen to the circuit? If this slip is 1 and this resistance appears as it is, this impedance of this branch is much lesser than the impedance of this parallel branch, which is the combination of the core loss resistance and the magnetizing current. So therefore this branch will dominate. Now if we apply a voltage which is close to the rated voltage, the impedance is so low that the machine will burn. Alright, the machine will simply burn. So therefore, when we block the rotor of the machine, we gradually increase the voltage, very gradually, until a current flows in this stator which is equal to the rated current of the machine. Right? So for example, every machine will have a rated power and has a rated voltage. From the rated power and the rated voltage, we can calculate the rated current. So all we have to do is increase this source voltage very gradually until the current flowing in the stator is equal to the rotor, is equal to the rated current. And this voltage is usually very low because, as I said, once you clamp the rotor and the slip is 0, this impedance is so small that you do not need much of a voltage to pass a rated current in the stator. Alright, and because this voltage is so small, the result is this parallel branch, which is composed of the rotor, of the rather core loss resistance and the magnetizing inductance, is negligible. The reason is because the voltage is so small, the magnetic flux which is produced is almost negligible. And because the magnetic flux produced is negligible, the result is we can neglect this parallel branch. It's as good as this entire branch in series. That's all there is. Right? So let's write this down. We have the blocked rotor test. And in this blocked rotor test, the rotor is clamped. Cannot move. Cannot rotate rather. And because it is clamped, the slip, actually I should write, NR is equal to 0. The rotor cannot move. And because the rotor cannot move, S is equal to 1. And therefore, just in this way, I'm just copying whatever is being done here. RR dash divided by S is equal to RR dash. And this is very small. Right? So now the question is, what are we trying to do here? We are applying VSRC such that the current IS is equal to rated current of the motor. Right? This is what we're doing. So if the current is the rated current of the motor, the ohmic loss, which is the loss produced by the current flowing through this stator winding resistance and the rotor resistance, is equal to the rated ohmic loss. This is the major loss major power loss under these circumstances, right? That is all the power which is being consumed by the motor It is not doing any mechanical work because remember, rotor is clamped. If the rotor is clamped, there is no mechanical output. So which means all the power which is being supplied by the source is being absorbed by the stator resistance and the rotor resistance, right? So therefore the power is equal to, let's call this IS. I can call this IS because we know IS is equal to the rated current. IS squared into RS. Let me call this RS. I think it's capital R, no, it's small r, so let me write it RS. RS, and also have to take into account IS raised to 2 into RR dash, right? Because remember, as I said, this parallel branch is negligible because the voltage is so small, there are no core losses and there is no magnetic field. So therefore this branch is negligible. We have a series branch here. So all the power is absorbed by this stator resistance and the rotor resistance. So now that we have this, actually there is an equal to sign, it's a mistake. Okay, that's a mistake. So it is a sum of these ohmic losses. So usually when we perform the blocked rotor test, it is possible to measure this power, right? It is possible to measure the power loss, and this power loss is equal to this combination. Now I'll talk about the relationship between this very soon, but before that we also have measured VSRC, right? Because we are controlling the amount of source voltage that we are applying. It's very important to note, source voltage is not equal to the rated voltage. When the rotor is blocked, you do not want to apply a rated voltage to the induction motor. It will burn. So you have to gradually increase it. So this voltage is a very small voltage, and this small voltage is producing this current IS, which is rated current, right? The result obviously is this impedance, right? Let's call this series impedance, right? We're just giving it a name. This series impedance is all these components together, that is RS, LS, LR dash and RR dash, right? It's simple Ohm's law. We can measure the voltage that we are applying and we can measure the current, and we know that the current is equal to the rated current, right? That is equal to the impedance. The reason why I'm writing Z is because there is a combination of stator resistance, stator inductance, leakage inductance, rotor inductance and rotor resistance. So it's not just resistance or inductance, it's a combination, which is where we have to take Z series into account. Now the question is, what is this Z series? Z series is equal to, okay, now it might get a little messy because this is going to be a square root sign, so I will just put this in bracket. Alright, I'm going to leave some space, but imagine everything inside this is under a square root sign, right? So under the square root sign there is RS squared plus XLS squared plus XR dash squared plus RR dash squared. And it's very important, do not forget these dashes. Remember, in this equivalent circuit, all the rotor parameters are being referred to the stator. So do not forget this dash. They are not the actual parameters. These are the referred parameters, right? So now we have two equations. We have an equation for power and we have an equation for series. That is impedance. This can be calculated. Remember, we are measuring the source voltage. We are measuring the current, right? The current is simply equal to the rated current. Therefore, this Z series quantity is calculated. This is a known quantity. This known quantity is equal to this expression. Now, again, we can make some assumptions. And the assumption is, we can say that XLS is equal to XR dash, right? That is, we are saying that the stator leakage inductance is equal to the referred rotor leakage inductance or other rotor inductance. In this case, the rotor inductance is the rotor leakage inductance. Right? We are saying these two are equal. Now, in reality, they may not be equal, but it's important to understand that these are very small quantities. Leakage is a very small quantity, right? Typically, leakage inductance is around 1 to 2% of the rated impedance, or rather the base impedance of any system. So we're talking about a very, very small inductance. We are simply equating these two inductances. So now the question then arises, we can replace this with just one variable. We got rid of one variable. Now, the last is this one RS and RR dash. Now, RR dash is the impedance of the rotor bars, right? Now, as I said, depending on what you have, if you have a squirrel cage induction motor, the rotor consists of bars which are short circuited on both ends. If it's a wound rotor inductor, then there is a rotor winding which is taken out as slip rings, and there can be an external resistance connected, right? But let's consider a squirrel cage induction motor at the beginning. RS is the winding resistance of the stator. This is the stator coil or the stator winding. And RR dash is actually the bar resistance, the rotor bar resistance. So we cannot equate these two. We cannot say RR, let me write this down. I cannot say, now how do I say not equal to? Typically the programming language for this is no exclamation mark and equal to, but it's important to say RS is not equal to RR dash, right? That is, the stator winding resistance is not equal to the rotor resistance. Here we need to separately estimate them. Now, again, we can make reasonably good estimates just by assuming, for example, we can say that this rotor stator winding resistance is around 0.5 to 1% of the rated impedance, right? So for example, I could say that if rated current flows through the stator, alright, the rated current, then the voltage can be equal to, let's say, 0.5%, right? That is 0.005% of the rated voltage. Now again, this is an estimate. You can change this value. If you want, you can say that this is 1%. So I can make this 1%. If you really want to go crazy, you can say 2%. That's too much, right? If a rotor resistance has 2% voltage drop, that's quite a bad rotor, quite a bad machine design. So I would say 0.5% to 1% is a reasonable estimate for this, right? And just to be clear, let me write this down, is 1% or rather 0.5% of rated impedance. Right? What that means is, if the rated current flows through the stator winding resistance, it will produce a 0.5% voltage drop of the rated voltage. Alright. So with this, we can estimate RS. Right? RS can be estimated from this equation. And once you have estimated RS, you can put it into this equation and calculate RR dash. All that's left is, we have RS, we have RR dash, and we have one variable remaining, because we have assumed XLS and XR dash, right? You can actually even write this as X, all right? So there's one equation, one variable remaining. And all we have to do is to estimate this one variable using all other known quantities. So with this, we have calculated all the other parameters of the induction motor equivalent circuit. For example, we have estimated RS, that is the stator winding resistance. Right? Again, you could say that we kind of cheated, because we are estimating it not using the block rotor test, but rather using our own ballpark numbers of what we can expect. This is reasonable in an induction motor. So again, this is kind of cheating, but it is reasonable. So we have come up with a value for RS. We have come up with a value for LLS from this equation, right? This calculation. So we know the stator leakage inductance. We know the rotor inductance as well, because it's the same as the stator inductance, and we've also calculated. And we know the rotor resistance, which is calculated from the loss. And since we already know the core loss component and the magnetizing component from the no load test, we now have all the parameters of the equivalent circuit of the induction motor. Right? So if you are a student, if you have a machine and you have a laboratory with which you can perform these tests, using the no load test and the block rotor test, you can estimate all the parameters of the equivalent circuit of your motor. Right? Now, in this simulation series, quite obviously, I cannot perform a no load test and a block rotor test. So I'm going to assume some values for all these, right? Fairly reasonable values. And I'm going to use these values in the simulation model. All right. So with this, I'm going to end this lecture. In the next lecture, we are going to gradually start translating all these into a Python code. That is, I want to show you that how this equivalent circuit is not only just useful for analysis and the understanding of a motor, but we can actually use this equivalent circuit for simulating an induction machine. Again, we are quite a long distance from simulating an induction machine. I'm going very gradually. So step by step, we're getting closer. So if you have any doubts, please do post either in the comments or send me an email or message me on social media, whichever is your preference. Otherwise, I will see you next week where we will continue and I'll expand on what we can do with this equivalent circuit. Thank you so much for watching and see you soon. Goodbye for now.